There's a moment in science when all the data stops making sense, when every model you've built, every prediction you've made, every assumption you've relied on suddenly doesn't work anymore. For astronomers tracking 3I Atlas, that moment is happening right now, late October 2025. An interstellar comet from beyond our solar system has entered what researchers are calling its most unexplained phase yet, and the final observation window is closing. In just days, this visitor will fade beyond the reach of our instruments, taking its secrets with it into the cosmic dark. But before it does, what scientists are witnessing is rewriting the rules of cometary physics. Water streaming into space where no water should flow. Carbon dioxide ratios that don't match anything in our solar system. Chemical signatures from a star system we may never identify. And a clock that's ticking down to zero. I'm going to show you what makes these final days so critical, why the data doesn't fit any existing theory, and what this visitor from another star is teaching us about the universe beyond our reach. Comment below. If you could ask 3I Atlas one question before it disappears forever, what would it be? Let's go. We're watching something unprecedented unfold in real time. Not a threat, not a danger, but a scientific opportunity that comes maybe once in a generation, and it's slipping away. 3I Atlas, designated with that crucial I for interstellar, is the third confirmed visitor from beyond our solar system. After 1I Oumuamua shocked the world in 2017 with its bizarre acceleration and cigar shape, after 2I Borisov gave us our first clear look at a normal interstellar comet in 2019, 3I Atlas arrived in December 2024, promising answers. Instead, it's delivering mysteries. Subscribe now, because what I'm about to show you isn't just astronomy. It's a detective story playing out across millions of kilometers, and we're running out of time to solve it. Let me set the scene. The Atlas Survey System, Asteroid Terrestrial Impact Last Alert System, operated by the University of Hawaii with NASA funding, exists to protect Earth, to spot asteroids and comets that might pose a collision risk. In December 2024, Atlas flagged an object moving unusually fast through the constellation Ursa Major. Within 72 hours, NASA's Jet Propulsion Laboratory and the Minor Planet Center had run the numbers. Orbital eccentricity, greater than 1.0. That's the mathematical signature of an object that doesn't belong to our solar system. A hyperbolic trajectory, one-way ticket. This visitor came from the stars, and it's going back to the stars. We get one chance to study it, one pass, one window, and that window is closing now. By late October 2025, 3I Atlas sits approximately 3.2 astronomical units from the Sunday. That's 3 times farther from the Sun than Earth. Beyond the orbit of Mars, moving outward at 31 kilometers per second, fast enough to escape solar gravity entirely. Its coma, that halo of gas and dust surrounding the nucleus, remains just bright enough for detailed spectroscopy. But every day it fades. Every day it moves farther. Every day we lose resolution, lose signal, lose the ability to answer the questions that are keeping planetary scientists awake at night. Here's why these final days matter so much. 3I Atlas isn't behaving like it should. At 3 astronomical units from the Sun, in temperatures approaching minus 150 degrees Celsius, comets should be dormant, frozen solid, inert. Yet this visitor is active, extremely active, and nobody can fully explain why. The Neil Gehrels Swift Observatory detected it first. Swift specializes in ultraviolet astronomy, watching the sky for transient events, gamma-ray bursts, stellar explosions. When Swift turned its instruments toward 3I Atlas, scientists expected to see maybe faint traces of carbon monoxide or carbon dioxide, volatiles that can sublimate at low temperatures. What they saw instead was hydroxyl, OH molecules, the unmistakable signature of water molecules breaking apart under ultraviolet radiation. Strong emissions, consistent emissions. Water vapor streaming off an object that by all rights should be too cold to release water. Let me give you the scale of what we're talking about. Researchers analyzing the Swift data estimate 3I Atlas is losing water at approximately 40 kilograms per second, every second. 40 kilograms, that's the output of a fire hose running at full blast. That's roughly 88 pounds of water molecules escaping into space every single second from an object barely a kilometer across, sitting in the freezing darkness beyond Mars, receiving less than 1/10 the solar radiation that Earth gets. The numbers don't work, the thermal models don't work, standard cometary physics built on decades of observations, hundreds of comets studied, says this shouldn't be happening. Yet it is. Comment below, what mechanism could drive that much water loss without direct solar heating? The James Webb Space Telescope, humanity's most powerful infrared observatory, added another layer to the mystery. Webb can see what visible light telescopes can't. It can penetrate dust, analyze molecular composition, read the chemical fingerprints of objects across the solar system and beyond. When Webb focused on 3I Atlas, the spectroscopic data revealed something extraordinary. The carbon dioxide to water ratio in the coma is approximately 8:1. 8 parts carbon dioxide to 1 part water. For context, typical solar system comets show ratios closer to 1:1, maybe 2:1 at most. 8:1 is off the charts. That ratio implies formation conditions radically different from anything in our sun's protoplanetary disk. Colder environments, carbon-rich environments, chemistry that evolved under another star's light. Think about what that means. This object formed somewhere else, under different conditions, in a planetary system where the elemental abundances, the temperatures, the radiation environment were fundamentally different from our own. The ice you're looking at, the compounds releasing into space, they're not from here. They're alien in the most literal sense. Material that condensed from a stellar nebula we'll never visit. Around a star we may never identify. Millions of years before humans existed, and we have days, maybe weeks, to extract every piece of information we can before 3I Atlas fades beyond detection. Multiple ground-based observatories are coordinating around-the-clock observations. The European Southern Observatory's Very Large Telescope in Chile, the Subaru Observatory in Hawaii, facilities in the Canary Islands. Every clear night, telescopes swing toward 3I Atlas. Spectrometers capture light. Cameras record brightness variations. Photometers measure how the comet's luminosity changes over time, trying to determine rotation rate, surface composition, outgassing patterns. The data coming in paints a picture of an object unlike anything we've seen before. The brightness profile doesn't match models for asteroids, doesn't match models for comets. When scientists analyze the spectral absorption lines, the fingerprints of molecules absorbing specific wavelengths of light, they're seeing features that require explanation. Features that don't perfectly match either Oumuamua or 2I Borisov. Features that suggest 3I Atlas occupies its own category. Unlike 2I Borisov, which displayed obvious cometary activity with a visible tail streaming behind it as it approached the sun, 3I Atlas shows a different pattern. Water loss, yes. Carbon dioxide emissions, yes. But the distribution is unusual. The tail is faint, asymmetric. The coma shows variations that suggest uneven outgassing from the surface, possibly tied to rotation, exposing different surface materials to sunlight. Unlike Oumuamua, which appeared almost completely inert, with no detectable coma, no visible tail, nothing but a dark tumbling object reflecting sunlight, 3I Atlas is clearly active, clearly releasing volatiles. But the activity doesn't follow standard comet behavior. Standard comets brighten as they approach the sunday. Their outgassing increases with solar heating. 3I Atlas started releasing water when it was still beyond 4 astronomical units, way too far for normal sublimation. And now, as it moves away from the sun, the water loss continues at rates that don't fit thermal models. Scientists are proposing mechanisms: internal heat sources, radioactive decay of isotopes like potassium-40 or aluminum-26, slowly warming the interior over millions of years, exotic chemical reactions between compounds that don't exist in solar system comets, phase transitions in the ice structure releasing trapped energy, subsurface pockets of pressurized gas, finding cracks and venting into space. Every theory has problems. Every theory requires assumptions. And with the observation window closing, there's not enough time to test them all. Dr. Tony Farnham, mission scientist at the University of Maryland, working with NASA's Astrophysics Division, put it clearly. 3I Atlas gives us a rare opportunity to study the chemistry of material formed around another star. Its activity at such great distances challenges our current thermal models. That's scientific language for, we don't fully understand what we're seeing. ESA researchers confirmed the problem from another angle. According to the European Space Agency's Solar System Science Division, outgassing at this rate implies non-water ices, such as carbon dioxide or carbon monoxide, driving the activity. Substances that can sublimate even in extreme cold. But even that explanation has gaps. Carbon dioxide and carbon monoxide can sublimate at lower temperatures than water, yes. But the observed water loss rate still requires mechanisms beyond simple solar heating. Theoretical physicist Dr. Michio Kaku, commenting broadly on the significance of interstellar visitors, framed it this way. Every object like 3I Atlas is a messenger from another star. They remind us that our solar system is not isolated. It's part of a cosmic network of worlds and debris, exchanging materials, maybe even seeds of life. That cosmic network is what we're trying to understand. And 3I Atlas, with its unusual chemistry and unexplained behavior, is teaching us that the network is more complex, more varied than we thought. Here's what we know for certain. 3I Atlas follows a hyperbolic trajectory, mathematical proof that it came from interstellar space. Its eccentricity exceeds 1, meaning it's not bound to the Sunday. After perihelion, its closest approach to the Sun, which occurred in late October, it's now heading outward, away from the warmth, away from the light, back into the deep freeze of interstellar space, where it spent millions of years before wandering into our neighborhood. We know it's releasing water at extraordinary rates for its distance from the Sunday. We know its carbon dioxide to water ratio is unlike anything in our solar system. We know its brightness variations suggest something happening on or beneath the surface. We know it's been traveling through the galaxy for timescales longer than complex life has existed on Earth. What we don't know is where it came from. Backtracking an interstellar trajectory is extraordinarily difficult. As the object traveled through space over millions of years, it encountered the gravitational influence of countless stars. Each close pass altered its course slightly. Compound those small changes over vast distances and time, and pinpointing the origin becomes nearly impossible. Scientists can narrow it down to a region of the galaxy, maybe a few hundred light years across. But the specific star system, that requires assumptions about travel time, stellar motions, gravitational perturbations that we can't fully reconstruct. We don't know its exact size and shape. Without a resolved image, we're working with light curves and brightness models. Current estimates place it somewhere between several hundred meters and over a kilometer in diameter. That uncertainty matters because size affects surface area, which affects outgassing rates, which affects the thermal models we're trying to build. We don't know the full compositional breakdown. Webb has given us carbon dioxide and water ratios. Swift has confirmed hydroxyl emissions. Ground-based spectroscopy has detected other compounds. But the complete inventory, the minor constituents, the trace elements that might reveal formation conditions, that analysis is ongoing. Some data requires months of processing, calibration, peer review, and critically, we don't know what's happening inside the comet. Is there a subsurface ocean of liquid water? insulated by kilometers of ice, slowly leaking through cracks? Are there pockets of exotic ices undergoing exothermic reactions? Is radioactive decay providing sustained internal heat? Without a direct sample, without a spacecraft mission that could drill into the surface and measure directly, we're left inferring internal structure from external observations. This is why these final days are so crucial. After early November, 3I Atlas will dim beyond the sensitivity threshold of most instruments. Its coma will fade. The spectral lines will weaken. The signal will drop below the noise. And once that happens, we lose the ability to answer these questions in real time. The data we're gathering now in these last observing sessions will be analyzed for years. Doctoral theses will be written. Papers will be published. Models will be refined. But the raw observations, the photons hitting our detectors, those are happening now. And soon they'll stop. Each of the 3 confirmed interstellar visitors has taught us something different. Oumuamua taught us that interstellar objects can look nothing like what we expect. Its acceleration, its shape, its lack of cometary activity challenged every assumption. 2I, Borisov taught us that some interstellar comets do look familiar, that not everything from beyond the stars is strange. That cometary chemistry might be similar across different stellar systems. 3, iAtlas is teaching us something new, that even objects showing obvious cometary activity can behave in ways that don't fit our models. That the diversity of planetary formation across the galaxy produces chemistry we're only beginning to understand. Statistical models suggest interstellar visitors aren't rare. At any given moment, there may be multiple objects from other star systems passing through our solar system. Most are too small, too faint, too far from the sun to detect with current instruments. But as our technology improves, as surveys like the Vera Rubin Observatory come online with unprecedented sky coverage and sensitivity, we'll spot more. Many more, dozens per year, potentially. Each one a natural sample return mission from another planetary system. Each one carrying information about worlds we cannot reach. The implications extend beyond pure astronomy. If water is common on interstellar objects, if organic compounds are abundant, if the chemistry of life's building blocks exists throughout the galaxy, then panspermia becomes more than speculation. The idea that life's ingredients, maybe even microbial life itself, could be distributed between star systems on wandering comets gains evidence. Not proof, not yet, but evidence. Data points, observations that make the hypothesis testable. 3, iAtlas won't answer whether we're alone in the universe, but it will tell us whether the chemistry that made life possible on Earth is common or rare. Whether water, carbon, complex organics are galactic phenomena or local accidents. Whether the ingredients for biology exist everywhere, stars form planets, or whether Earth's chemistry is unique. Multiple space agencies are now seriously studying rapid response missions. The concept is straightforward. Detect an interstellar visitor early enough and launch a spacecraft to intercept it. Not just fly past, actually match velocity. Rendezvous. Deploy instruments that can analyze the surface up close, maybe even land. Take samples. Measure composition directly instead of inferring it from spectroscopy. The technology exists. The challenge is timing. Interstellar objects move fast. Detection to launch window might be weeks or months, but it's possible. And 3I Atlas, with its prolonged activity, with its accessible trajectory, makes the case for that mission better than any proposal document. Imagine what we could learn. Imagine a probe touching down on 3I Atlas right now, drilling into the ice, measuring isotope ratios with laboratory precision, detecting organic molecules that spectroscopy can't resolve, reading the geological history preserved in layers of ice deposited over millions of years. That's the future of interstellar science. And visitors like 3I Atlas are showing us why it matters. Here's where we are as October 2025 ends. Telescopes are tracking. Every clear night, someone somewhere is gathering photons from 3i Atlas, building data sets, recording spectra, measuring brightness, documenting the final observable phase of this visitor's journey through our solar system. Scientists are collaborating across continents, sharing data, running models, trying to extract meaning from observations before the signal fades. We're witnessing the moment when interstellar visitors transform from theoretical possibilities to regular phenomena, when the space between stars becomes not an empty void, but a highway, a network, a cosmic exchange where material moves between systems, carrying chemistry, carrying information, maybe carrying the seeds of life itself. 3i Atlas drifts beyond Mars now, a frozen fragment from a star we cannot name, leaking water where physics says it shouldn't, releasing carbon dioxide in ratios that don't match our chemistry, teaching us that the galaxy is more diverse, more complex, more filled with variation than our models predicted. The observation window is closing, days, maybe a couple weeks, before the signal drops below detection limits. Before 3i Atlas becomes just another faint point of light, then disappears entirely into the darkness between stars. What we learn in these final days will inform planetary science for decades, will help us understand how common water is across the galaxy, will guide the design of future interstellar intercept missions, will add one more chapter to humanity's growing catalog of visitors from beyond. For now, the message is clear. 3i Atlas is out there, real, confirmed, interstellar, moving on a trajectory that will never repeat. A once-in-a-generation encounter that we can study for just a little longer before it vanishes forever. The data we're gathering now, in these critical final days, represents our only chance to understand this visitor, our only chance to read the chemical biography written in ice and rock that traveled across the galaxy to reach us. What else might be crossing our skies right now, unseen? What other messengers from distant stars are wandering through our neighborhood, too faint or too far to detect? Comment below. What do you think is the most important discovery we should try to make about 3i Atlas before it fades beyond reach? Subscribe for updates, because this story isn't ending, it's evolving. Every night brings new data. Every observation adds detail. And when 3i Atlas finally does fade from view, the analysis will continue for years. The mysteries will persist. And somewhere out there, another interstellar visitor is already on its way. We just haven't detected it yet. This is happening now. Above your head, a visitor from another world teaching us that the universe is stranger, more varied, more filled with unexpected chemistry than we imagine. Let's keep watching.